Okay, off we go. So last time we were talking about rotations. So what I mean is equations with three variables, so representing surfaces in three dimensions, that are rotationally symmetric around an axis. So here was the observation that we made last time in reference to the equation. Right? So if x's and y's appear only as a part of this expression. Now that's, I want to emphasize, that is rare to happen, right? I mean, if you were to write down a random equation, what are the odds, right? And yet in the real world, it's surprisingly common. The world's full of circles is something I like to say a lot. It's a true fact. The world's full of circles. So when this happens, when you notice that in your equation, the only way that x and y appear is as part of that expression, then you get this powerful result that is rotationally symmetric around the z-axis. And again, the reason why, if you think about such an equation and consider this point, and then this point here, that's the result of a rotation around the z-axis, right? So these are different points, though, but they're related by one is a rotation of the other, or each is a rotation of the other. Well, it's tempting to say that, well, look, these are different points, and they have different x's and y's, and come on, when you plug in different numbers into an equation, what are the odds they're both going to work, or, neither going to work? It doesn't seem like there'd be any connection. But these x's and y's only serve to go into this expression right here, right? That's the only way that x's and y's show up, and by construction, that expression is exactly this distance, and these points being rotations of each other, those distances are the same, right? And then likewise, their z coordinate, because they are rotations of each other around the z-axis, those z coordinates are the same. So as far as the equation's concerned, the equation only involves this one expression in green for x's and y, and then z. That's it. And these 2 points agree. So either they both work or they both fail. And the nice punchline then is that that means that this surface is rotationally symmetric because all the points are effectively rotations of other points also on the surface. Okay, so that's the idea. Now let me give you a different point of view on this. This is kind of a cylindrical coordinates point of view. We didn't have time to talk about this last time. Think about what happens if x and y appear only as part of that expression. And in particular, let's think about how would this equation convert into cylindrical coordinates. Right? Now, when you convert, x is our cosine theta. And y is our sine theta. Right? And so you're like, all right, well, when I plug in for the x, then thetas are going to show up as a result of that plugging in. But the thing is, if the x's and y's, the possible sources of the thetas, if all they do is go straight into this expression, and if that expression is r, then they don't produce any thetas at all. There just aren't going to be any thetas in the equation. Z certainly doesn't make any thetas show up, right? And x and y will apparently only make r's show up. So this sort of an equation is a cylindrical equation, will be represented by a cylindrical equation that doesn't have any thetas in it. And we already talked about this. If there's no thetas, then theta doesn't matter. And that means all the theta cross sections look alike, and that means it's rotationally symmetric. So, two different points of view on the same result. Really powerful result then. And so here's how we're really going to use that in practice. When a surface has this symmetry, this rotational symmetry around the z-axis, then you can just understand its cross-section in any plane containing the z-axis. I mean, obviously if you're rotating around the z-axis. Let's look at any one of those cross-sections. And then just rotate that cross-section around the z-axis. Right? And this is a much easier thing to do than dealing with a three-dimensional equation. So let's take this one here, for example, and side note, now we did talk about this specific equation last time, and I kind of made some hand-wavy gestures along the lines of, well, it's kind of quadratic in x, if you will. right? And it's kind of quadratic in y, if you will. But that was all very hand-wavy and non-rigorous. So here's the way I'm going to treat it now. I'm going to observe that this equation is equivalent to z equals square root of x squared plus y squared, quantity squared. And having written it like this, notice, as required, the only appearances of x's and y's are as part of that key expression. So this equation represents a surface that is rotationally symmetric around the z-axis. Everybody with me? Okay. All right. Now, again, because it's rotationally symmetric, all I have to do is look in any cross-section. And by the way, I'm going to go ahead and erase this algebra here. By the way, the upshot of this little algebraic trick, by the way, is that when you see x squared plus y squared, that counts too, because that's the relevant square root squared. Right? So that works too. Okay. Okay, so we have a rotationally symmetric surface, and that means that I can just understand its cross-section in any plane containing the z-axis. Take your pick. Any plane you want. Free country. The world is yours. Now, I have a personal favorite plane containing the z-axis, and that is the YZ plane. And a lot of you might be thinking, why not the XZ plane? Well, the XZ plane, when you look at it, the XZ plane, you're kind of looking at an angle, and it's just a little more awkward to look at. So, again, my personal favorite, the YZ plane. So I'm going to say, let's look in the YZ plane. In the YZ plane, x is equal to 0. And when x is equal to 0, our equation is literally just a parabola. It's just z equals y squared. And there's nothing hand-wavy about this. I'm looking in a plane. I'm looking in an equation involving two variables. This is high school algebra. Z equals y squared is just a parabola. How we doing? Everybody with me? So looking in this cross-section, I get a parabola, and I know that my surface is rotationally symmetric around the z-axis, and so I'm just going to rotate the parabola around the z-axis, and I appeal to your geometric intuition. If you rotate that parabola around the z-axis, then you get a bowl like this. How we doing? Is everybody happy? All right. So I think this is a really powerful tool, really powerful trick for understanding, in some cases, as with all tools, they only work in certain cases, but surprisingly often, a very powerful tool for understanding an equation of three variables. And let's see some more examples. Alrighty, let's, if I can get these to erase, here we go. A little terminology, just so we can use this word going forward. The word is paraboloid, right? So anyway, but you can see the root parabola in there pretty clearly, and paraboloid is just how they distinguish it as being kind of a three-dimensional sort of thing. Okay, so let's understand this equation right here. What is that? And again, let's not move too quickly, but notice x and y in this equation, and I emphasize it's not just that x and y do appear as part of this form. It's that x and y appear only, exclusively, as part of this form. There are no other x's and y's anywhere in this equation other than as part of this form, and that means that I am rotationally symmetric around the z-axis. It's pretty sweet. Okay, so huge first observation that this is rotationally symmetric. Knowing that it's rotationally symmetric, again, I get to pick my favorite half plane. Now, just to show you it doesn't matter, I'm going to pick a different one. I'm going to pick now the XZ plane. Now, this does contain the z-axis. Again, of course, it's got to contain that's the symmetry that we have. So, of course, we have to look in a plane that's relevant to that symmetry. So, looking in the XZ plane, where, y is equal to 0. And if I plug in y equals 0, then my equation turns into this. And so what I really need to understand in this plane, I need to understand, well, let's see here, x squared minus z squared equals 1. And now I know high school algebra was a long time ago, and there's always this confusion, oh gosh, does it go this way? Or, oh my gosh, is it one of those other ones? Does it go this way? And how do you remember, etc.? So everybody's going to have a different point of view on that. Dust off your old high school algebra notes and remind yourselves how you like to think about that. But make sure that you're comfortable and proficient in being able to remember which way parabolas go based on the equation. I'm sorry, hyperbolas. And by the way, of course, if you're rusty on this, come to office hours. I'll be happy to talk to you about it. Okay? But anyway, that equation gives me this hyperbola. And again, I know that I'm rotationally symmetric around the z-axis. I know what one of the cross-sections looks like. So if I rotate that cross-section around the z-axis, then let's see here. Let me do it like this. Rotating around the z-axis produces this shape right here that I've drawn a rough sketch of there. How we doing? Everybody on board? By the way, just a reminder, I mean, this course is unavoidably and intrinsically geometric, right? So being able to visualize in 3 dimensions is going to be important, and very important to being able to visualize in 3 dimensions is to be able to draw in 3 dimensions, both to help you visualize and to communicate what you have visualized. Right, so drawing is just unavoidably important, and I remind you, if maybe 3D drawing is not something you've been good at in the past, now's the time to get good at it. Everything that I know about how to draw in 3 dimensions I have on these videos on my YouTube channel, Miscellaneous Topics playlist. I hope you'll give those a look if you think you might maybe need some help in that area. Do, though, take this as a pretty good example of the kind of thing I'm looking for. Notice that's not a computer generated quality. This is very sketch, right? I mean, it's just a sketch. But notice also, it pretty much communicates what this thing is. It's very effective for a couple of swipes of the pen, right? So this is a pretty good example to look at in terms of what the level of expectation is. But make sure that you can do this sort of thing. Okay. All right. Now, the argument that we've made so far has been for rotations around the z-axis. I'm going to say that there are similar arguments for rotational symmetry around other axes, and I'm going to leave those arguments to y'all to fill in the blanks on. I think it's a good exercise, but you can probably guess just by sort of, symbolic analogy what the rule is going to be. And so I'm just going to sort of dive in on how to use them. Now, at a glance, you don't see any variable squared plus other variable squared immediately in here, but notice that if you rewrite it, if you sort of distribute the minus sign here, right, then lo and behold, y and z appear in this equation only, not partly, but only as part of the magic expression, and so this is rotationally symmetric around the x-axis. So again, I'm leaving the argument there as an exercise. It's totally analogous to the one that we made about the z-axis. A nice exercise to think that through. Okay, so let's just proceed. If it's rotationally symmetric around the x-axis, there's the x-axis, and so I guess I can look for its cross-section in any plane containing the z-axis, and I got a bunch of options, I suppose. I could look at either of those two. If I were some sort of masochist, I suppose I could also look in like something like that. I don't know why we would do such a thing. That'd be harder, much harder to do. Let's just say we don't choose those kinds of planes. But we do have a couple to choose from. Arbitrarily, I'm going to choose this one. No good reason. Doesn't matter. Aside from the fact, of course, that it contains the axis that we're rotating around. And with this one being chosen, all right, well, in that plane, we have z equals 0. Right there in the picture. If z is equal to 0, we can plug that into the equation, and the equation then becomes that. again, high school algebra, hyperbola. You got to think it through. Make sure your high school algebra is sufficiently polished. Right? You can remind yourself that it looks like that. And now we ask ourselves, okay, well, what happens when I rotate that around the x-axis? And you just have to use your geometric intuition, but I claim that we get this. This is hard to draw, but this is my attempt to draw kind of. I like to think of it as being a contact lens. It just, to me, and I like to therefore call this surface casually. I call it the staring contest. Right? It's two people just eyes right up next to each other. I think it's weird, but anyway, it's funny. Anyway, that is the surface that you get. Now, this is these two surfaces that we've just talked about. Let's see if I can fit them both on. Well, anyway, close. This one, being a rotation of a hyperbola, is called a hyperboloid. This one being also a rotation of a hyperbola, this is also called a hyperboloid. Notice, however, two very different surfaces. So to distinguish them, we say this is a hyperboloid of one sheet because there's just one connected component there, right? Whereas this is, we call it a hyperboloid of two sheets. Again, there's two separate connected pieces to that surface. Okay, plausible? Questions? Pretty good. Okay, so here's another tool for how to understand equations of several variables. And well, I'm going to call this deformations. You'll see why in a second. So the question I want to address is if you have an equation and maybe you understand whatever reason, but you already understand what this equation represents, you already understand the surface that it represents. What happens if you replace everywhere in that equation that you have a z, you replace it with 2z? Let's just say. So for example, what happens to this equation here if there where I have a z, notice I just replace it with 2z? Reasonable question to ask, right? So if we understand the rule here, the big idea is if I understand a rule for, when I do this algebraic move, if I can infer what happens geometrically, then I can take equations that I already understand and kind of tweak them around using these rules that we're about to discover. And from this knowledge, I can infer that knowledge. That's the big idea. That's where we're going with this. Right? Okay, so let's actually do it though. What happens when I replace the z's with two z's? All right, so I'm just going to. This is a hand wavy argument. I think this gives the best intuition. But let's think about this point here: 3, 4, 12, and notice at that point satisfies that equation. A little arithmetic. Okay. Now I'm going to look at my new equation over here and ask, does that point satisfy, does that point satisfy this new equation? Well, no. Obviously. Of course not. We changed the equation. You change the equation, everything changed. Obviously it's not going to work. If it did, it'd be a weird coincidence. Okay, now let's take a moment, though, to think through what went wrong. I mean, this point works great in that equation. When I plug it into this equation, something happened. Something went wrong. And it's obvious, of course, what happened is that this 12 that went into here and just got squared, well, over here, this 12 went into here and it got multiplied by 2. Right, this 2 here turns that 12 into a 24 getting squared. Obviously, that's now everything's different. So the clever observation then is to say, okay, well, if we are going to be multiplying by 2, and if I know that the 12 going into there and getting squared worked, slick move, if I were to just consider 6 instead of 12, that 6 would go into there, it would get multiplied by 2 and turn into the 12 that we already know works. So this is kind of a smart alecky sort of move, right? But it works. Everybody see what happened there? Okay, so the takeaway I want to have on this is that when you do this algebraic move of replace all your z's with two z's, that algebraic move in effect turns this 12 into a 6, kind of, if you will. Let me say it differently. And a point there with z coordinate equal to 12 that no longer works could be thought of as being replaced by this new point that does work because of exactly the nature of the... Okay, so another way to say this is that having, in the algebra, having multiplied by 2 kind of, sort of, causes in the geometry the exact opposite to happen. The exact opposite, namely the z coordinates all get cut in half. To kind of account for the fact that there's an extra factor of 2 there. So that's my general rule. So what you do to a variable in an equation, the opposite is what you would expect to happen to the surface. Okay. So altogether then, because of that algebra, this surface has been smushed, right? It's been compressed in a vertical direction by a factor of 2. Okay. All right. So this is a pretty broadly applicable rule. And it works in the different directions, and it works if you, instead of replacing z with z times a constant, it works if you replace z with z plus a constant. Same kind of trickery, and it's just going to shift things downward. Right? So, all right, let's see some examples. All right, let's try to figure out what this surface looks like. I'm going to do that by starting with that equation. I know what this equation looks like, and why do I know what the blue equation looks like? Well, because that basically says rho equals 1. And rho equals 1, just, my understanding of geometry, distance from the origin is equal to 1. Okay, that's a sphere. That was an easy one. Right? Now, that was not my goal. I was not interested in that surface. I'm interested in this green surface over here. How am I going to use the given information about the blue surface to help me understand the green surface? Well, I'm just going to observe that even though they're different, I can get to the green equation by everywhere I see an x, replace it with x over a. And everywhere I see a y in this equation, I understand, I'm going to replace it with y over b. And everywhere I see a z, I'm going to replace it with z over c. And what's the opposite of dividing? Well, multiplying, right? And so we would expect that this, let's see here, I have colors, that this replacement here, replacing all the x's with x over a's, is going to stretch in the x direction by a factor of a. And the y substitution here is going to stretch in the y direction by a factor of b, and the z replacement is going to stretch in the z direction by a factor of c. And that gives us what we call an ellipsoid. In the same sense that when you stretch out a circle, you get an ellipse. When you stretch out a sphere, you get an ellipsoid. Everybody follow the argument there? Okay. All right. A couple more examples, and these are all really kind of morally equivalent, but if you take a paraboloid and stretch it out, that paraboloid that has circular cross sections, well, now it has elliptical cross sections, and so we call this an elliptical paraboloid. And let's see here. Likewise, here we had a hyperboloid. Well, you stretch it out, you get a elliptical hyperboloid. One little algebraic thing to be careful about. Do be careful. You are replacing the variable there right? And so when I say that, that turns into this, some students make the mistake of instead writing, let's see here, some students say, well, it was y squared, so now I guess it's going to be y squared over b, right? They see the y and they just put over b. But don't forget, effectively there are, let's see here, I got to get back to pencil mode. There is effectively parentheses there, and so you've got parentheses there, and so therefore, so when you square y over b, you get y squared over b squared. Right, easy to make that mistake, yes.
So if A and B were like the same value, would it still maintain like that value?
Yeah, that's right. If A and B were the same value, then you'd be stretching by the same factor in both directions, and then coincidentally it would be still circular. That's right. Yeah. Anybody else? Okay. All right, a few other examples in the book to take a look at. Let's see here. And with all of that noted, now we're going to actually start doing derivatives. By the way, notice we're skipping over section 2.2. This is another one of these things that makes me sad. It's really, arguably a very important section, 2.2 is. But it's very important from a mathematician's formalities kind of point of view, and that makes it something that I would love to talk about, but it also makes it something that, it's easily hand-waved, and it's extremely believable. And yeah, there are some interesting things that happen that you wouldn't expect, but in terms of the punchline of how are we going to, in practice, be using calculus, it can pretty readily be swept under the rug. And so, sadly, skipping 2.2, y'all are not responsible for 2.2. And we're moving on to 2.3. Okay. All right, so the derivative. Now, this is obviously a very important topic, how to take derivatives in multivariable functions. First thing to say is there are lots of kinds of derivatives, and so this is one of the big differences between single variable calculus and multivariable calculus. In single variable calculus, there's the derivative. End of story. Right? And I guess you could say there's like a second derivative, third derivative, but that's really just the derivative of the derivative. So there's really, morally, there's only one kind of a derivative in single variable calculus. In multivariable calculus, there are several. So when you have multiple things that we use for which we use the same word, namely a derivative, that means that they have to have something in common. Why do we use the same word for different things? Well, they have this common, what I like to call a unifying feature. And I think this is an important thing to hit before we talk about any actual derivatives, is what is it that unifies them? What makes them all derivatives? And it's this thing right here. They relate input changes to output changes. There's, of course, different ways that you can say this. I think this is the most pithy and intuitive. When you have a function, you can change the input values. And then you could reasonably ask, well, what does that do to the output values? Right? And that's what derivatives are all about. Okay, so these multiple different kinds of derivatives will relate input changes to output changes in different ways and in different cases. But they all have this feature that they relate input changes to output changes. Okay, all right, now that said, we are going to dive in and pick a derivative and go with it. I'm going to use the same choice here that the book uses. This is also the choice that's made by most books on multivariable calculus. We're going to start with partial derivatives. Now, why are we going to start with partial derivatives? There's some great things about partial derivatives. I'm a fan, don't get me wrong. They are easy to compute. We'll see that momentarily. They're easy to relate to what you already understand, namely single variable derivatives. So they're familiar. And that's great. These are good reasons to want to do it. And then, the third kind of a logistical reason, I'm going to start with these because the book does, and I could diverge away from the book, but then oh god, that creates complications, and that's just not really worth it. So here we go. We are going to start with partial derivatives, but word of warning: if we were using my book, we would not be starting with partial derivatives. My book does not start with partial derivatives because I don't think it's really the mathematically natural first thing to do when you're trying to relate input changes to output changes. And certainly, whatever order these topics are presented in terms of your primary point of view, like when you leave this course and someone says, what's the derivative of a multivariable function? What is that cornerstone, fundamental, basic idea of what a derivative truly fundamentally is? I don't think your answer should be partial derivatives. It's something different that will develop, and we'll get there. And so anyway, the risk, the danger of starting with partial derivatives is it might kind of lure you into what I think is a fundamentally bad point of view about multivariable derivatives. So please do not hang your hat on that this is what a derivative is and everything else is stuff that we build up for convenience. This is a tool that's a nice foot in the door, but we're really going to take a fundamental shift very soon on how we think about derivatives. So that's just a word of warning. And with all that warning out there, let's dive in. Here's how we do partial derivatives. The big idea, it's really a pretty simple idea. We're going to just choose momentarily to view most of the variables as being constants. Again, we can just decide, okay, I'm going to pretend. This is make-believe. And when you're doing make-believe, you can make-believe whatever you want. I'm going to make-believe that most of the variables in our function are actually constants. And if you think about it, if you have a bunch of variables and you hold most of the variables constants, except for one of them. So you used to have a bunch of variables, now you have a bunch of constants and one variable. Effectively, and so morally, you now have kind of a single variable function. Now again, this is all make-believe, right? We're pretending, we're choosing arbitrarily to make this choice. But because we now have a single variable function, well, we know how to take regular derivatives. When you have a single variable function, we're experts in taking single variable derivatives. You all know the power rule and the chain rule and the product rule and all that stuff. Right? You know how to interpret single variable derivatives, etc. So we're in business here. And this is called a partial derivative. And now we'll make some geometric interpretations in a minute. First, some notation. Partial derivatives are denoted like this. Note this symbol right there. It looks kind of like a D. Very importantly, it is not a D. You cannot write df over dxi. That's not okay. That's a problem and unacceptable. Right? You can't do that. Also, it does kind of also sort of look like a lowercase Greek letter delta. Importantly, it is not. And again, you can't use that either. Not okay. Right, so be sure not to misdraw this symbol. Now, you may possibly have never drawn that symbol before, and you might find it appropriate use of your time to practice. Just kind of start. Just give yourself a little handwriting practice, like you used to do in 3rd grade, right? Just get comfortable with how you personally are going to choose to make this symbol. But you got to make sure that it does not wrap over like that. You can't do that. That's not okay. Okay. All right. So there's the notation, and of course, not hard to imagine that people would want to rewrite it like that. I think it's an easy pitch. And then kind of, y'all remember, of course, also from single variable calculus that, df dx in single variable calculus is sometimes written as f prime. prime just being a shorthand for, derivative of that function. Well, we can't really do exactly that because there are several different choices of which variable I could choose to not be a constant. Right? I got a bunch of choices. So prime doesn't indicate which choice it is. So making a subscript is kind of the analogous Newton-like notation for partial derivatives. Subscript gives you the option to indicate exactly which variable you're taking the partial with respect to. Okay, everybody good with the notations? All right, so we are in business. Let me show you how to compute some of these things. Let's take this partial derivative right here, and I'm going to step back for just a moment to recognize that looks really hard and inconvenient. Oh my gosh, there's 3 factors and there's a cotangent. Oh, but it's a cotangent of a product that has an exponential in it. It feels like we're going to be doing a lot of chain rule. Oh, product rule. Oh man, gosh, so we're going to fill up half a page dealing with this. Doesn't that look scary at a glance? But remember, now we are taking a partial derivative, and it says right here, partial derivative with respect to y. That means y is our variable. That means, and again, partial derivatives, that means all the other variables are to be viewed and treated as constants. So, x and z, because y is our variable that we're taking the partial with respect to, x and z are constants. So, x and z being constants, that means with that x being constant, well then e to the x is a constant. And with x being constant, that means x squared is a constant. And with z being constant, that means e to the z is constant. That means this product is constant. That means its cotangent is constant. So what we've got here, we're taking the y partial not of a massive inconvenience. We're taking the y partial of y squared times a constant. An ugly constant, to be fair. But it's a constant. And we have very convenient rules, of course, for what happens when you take a partial derivative of something times a constant. And when you take the partial derivative of something times a constant, you just ignore the constant and take the derivative of just the something. And of course the constant comes along for the ride. Right? So all of this constant business still there. But the action only happened on the stuff that's not constant. And then, of course, you can rewrite. I mean, we typically like to put our actual numerals, out front. That's just an aesthetics thing. In some sense, nothing really happened there. So how are we doing there? Everybody see how this one worked? Okay. All right. So this example in mind, I propose this means that partial derivatives are just like single variable derivatives, except even better because I get to basically ignore, right? By treating as constants, we're basically ignoring a huge amount of the complexity that at a glance looks like there is in that function. So I think partial derivatives are even easier to compute than single variable derivatives. Because I get to just pretend I'm going to ignore all this stuff over here. It's awesome. Very convenient. Everybody with me? All right. A couple of more examples just to drive it home. This one here, at a quick glance, looks like a logarithmic differentiation problem. By the way, while we're on that, I know that very few of y'all have seen, certainly very few of you have retained this tool called logarithmic differentiation. I do think it's a pretty neat trick. And it's another thing that I think it's not hard. It's just a clever little idea. And if you don't know how to do logarithmic differentiation, it's another one I have a video of on my miscellaneous topics playlist. Give it a look. It's like 10 minutes. I forget. It's not much. And it's an easy trick. Okay. So that said, this looks like a hard problem. We have a function to the power of a function, but x is my variable, and that means that really this is the only actual function. And this right here, y, is, of course, a constant. And that means that y squared is a constant, and I'm just going to treat it like a constant. I'm going to, as we do with constants, when you're taking a derivative, you just bring it down, subtract 1 from the exponent. It's power rule. And, of course, don't forget the chain rule. Everybody good with that one? Okay. I hope it goes without saying, make sure that you're fully polished with your single variable differentiation skills. And you could probably see it coming that in a couple of chapters we're going to need you to be fully polished on your anti-differentiation integration skills as well. Okay, let's see here. Likewise, here now with this next one, we're taking a z partial, and there's a z there. But z being the only variable means that x and y are constants, which means all of this down here is constant. And so this is just, I'm taking the derivative of a constant to the power of the variable. And this is an old rule, right? Constant to the power of the variable. The derivative is constant to the power of that same variable, and don't forget to multiply by the log of that constant. Think of this as we're taking the derivative of a to the z. A is a constant, and this is the rule. Again, going back to a single variable. Everybody happy? Okay. Okay, now, we are in a weird position at this point with partial derivatives. I have made up a rule, and we've exercised that rule, and we've made up a notation, and it remains, at this point, that a critical outsider could look at this and say, okay, but you did make this up. This is totally arbitrary. And what does it mean? And if it doesn't mean something geometrically natural, then what good is this? Right? Why would I care about this make-believe scenario of I'm just going to pretend that these variables are constants? Right? The natural retort is, yeah, but they're not. Right? So, does this mean anything natural geometrically? Well, it turns out that, yeah, it does. Now, what it means geometrically depends on what kind of a picture you're looking at. And so this will, whoops, bad color choice. This is an example of a situation that I warned you all about. Last time we were talking about, graphs and level sets and the literal picture of a function, and then let's not forget that parameterizations, have an image. And so with all these different connections between algebra and geometry, no surprise, calculus is going to look different in all of them. And partial derivatives are a nice sort of first example. So I emphasize here for this first discussion that we're going to do. This first discussion is just about graphs, and eventually I'm going to leave it to y'all to be sort of in charge of, in your own mind, when we're doing things to have made the adaptation for yourselves to always consciously think about what kind of a picture are we looking at. Right? But I'm emphasizing it here just as a kind of a reminder. So, okay, if we're looking at graphs in this scenario, what are the geometric interpretations? Said differently, what we're about to do here is study the calculus of graphs. A little bit of calculus of graphs. Calculus of level sets will come later. Okay, so here's our scenario. We've got a function of two variables. Right? You can see that I'm looking at a graph because I've set the value of the function equal to a third variable. Right? Looking at a graph of a function of two variables, so surface and 3 space. And let's focus on a particular point on this graph. We're going to focus on that point on the graph. Keep in mind that point on the graph sits above a certain point in the XY plane. This point here, AB, representing the inputs, right? Those are the inputs that give rise to this output, Z, the combination of which give us x comma y comma z, which is the purple point there. Okay, so that's our setup. Is everybody with me? Alrighty. Okay, so we're going to ask the question, what is the geometric interpretation of the y partial of this function? Y partial. Oh, and I emphasize the y partial evaluated at this point, namely this x and y where I'm looking at the value of the function. Okay, so what is the y partial? All right, well, good news. When you're taking y partials, there are various steps in the process of computing the y partial, and the good news, each of those steps has a pre-existing geometric interpretation. And all we have to do is kind of walk through and just note what the geometry means in each of those cases, for each of those steps. So here we go. First step in taking the y partial is to fix all the other variables, which of course, x and y are the variables. And if we're leaving y as a variable, the other variable is just x. So we're going to fix x. And of course, x was, at the point in question, x is a. And so if we're going to fix x, that means we're going to just fix x at the value a. And so with that value a, we're going to fix x. And here is our first geometric interpretation. Setting x equal to a constant is a vertical cross-section that points kind of in the y direction, if you will. So it points in the y direction because x is what we're setting equal to a constant. What do you think? Everybody see it? Okay, so vertical cross-section is part of our answer. So let's see here. Now, next question. What's the next thing we do? The next thing we do is we take... I should come back up here for a second. We take the derivative of the resulting single variable function with respect to y. Well, that resulting single variable function, and keep in mind, we initially had z was f of x comma y, but we have chosen to fix x. So really, looking in this cross-section, in other words, looking at this curve right here, what we really have is that z is a function of just y. And this output value, z, is what represents height for us. Oops. Right? Z represents height. So this orange cross-section is literally the graph of our new single variable function. Thinking of z as a function of only y, x being a constant. So we're confined to this cross-section. Height is the variable z. This is a graph. Right? So, well, when we take a single variable derivative, when we take a, let me do this in blue now. When we take a derivative with respect to y, right? Y is our variable. We're taking a single variable derivative. We're looking at a graph. And what does a derivative look like? A single variable derivative. What does it look like on its graph? It's the slope. Slope of the tangent line. So at this point, we're just going to be looking at a tangent line and asking what its slope is. And that's it. So at that point, well, I didn't get the angle quite right there, but anyway, there you go. Slope of the cross-section. Slope of the tangent line to that cross-section is the geometric interpretation of that partial derivative. Okay. All right, so here you go. Partial with respect to y, slope of the tangent line to the graph. Very familiar, right? Now, I told you this was going to look a lot like single variable calculus, and again, it really does, doesn't it? I mean, this is a kind of a derivative that gives us a slope. So, very, very familiar. Points to keep in mind: y partial, and so slope in the y direction. Got to be looking at the cross section in the y direction because it's a y partial. Also keep in mind, and I already made a big deal out of this, but I'm going to do it again real quick. Don't forget this only works if you're looking at a graph. Right? Very, very importantly, only if you're looking at a graph. If you're looking at level sets, this is totally different. Totally different. Slope of the tangent line, this part here I think is pretty familiar. So, yeah. Okay, now an exercise I'm going to leave for y'all, just to think it through, is that if you take the partial with respect to x, again, slope of the tangent line to the graph, just like in the previous case, this time in the x direction. I think it's pretty easy pitch, but I think it's a great exercise to think through that picture. So give that a look. Good to see y'all again. I hope you had a good weekend, and see you on Wednesday.